Hi everybody, my name is Alfonso Flores and I am one of your biochem tutors here at the University of Texas at Dallas. Alright, let's begin. So welcome to Biochemistry, and one of the most popular images that your professors like to show at the beginning of lecture is this one, the one with the monkey and the looks to be a flower. I'm not too sure. Doesn't really matter. What you should be taking away from this image is that the biochemistry is shared between these two things. So they're both eukaryotes, and so as a result of that, a lot of the biochemical processes that happen within this monkey actually happen in this plant as well. So in Bio 1, you learned about glycolysis and the Tca cycle and a bunch of other stuff. Well, the way that it happens with the monkey is the way that it happens with this flower. I'm pretty sure that I'm butchering some of the terminology here, but that's the main idea. If it happens within the monkey, it happens within the flower because they're both eukaryotes. And so, yeah, so here we have an animal cell. You know what a cell looks like. I just included that because I thought it would look nice. Alright, and so this is a metabolic map. Don't freak out when you look at this image. I know that when I saw it, I was like, damn, like, do they really expect me to like memorize all this stuff? Well, the answer is no. At least the answer is no, unless you plan on taking Biochem 2, because if you do, good luck. But what you will be covering in this course is this pink pathway, which is actually glycolysis, and also this right here is the Tca cycle. And later down the line, it's the electron transport chain. So essentially, going back to the whole monkey and the flower thing, the way that these biochemical processes happen in the monkey is the same way that they happen in the flower. And if you took Biochem 1 or Bio 1 and Bio 2 here at UTD, then you've had the pleasure of meeting Dr. Shrikant and Dr. Wilson. These are our gods. And the reason why I say that is because the stuff that you learned with Dr. Shrikant and Dr. Wilson is extremely important here. So glycolysis, Tca cycle, electron transport chain, as well as the blood buffer system, and a bunch of like the other Bio 2 stuff that Dr. Wilson covered, it's all coming back. So is OChem and GenChem. So just so you know, Biochem 1, it's going to be a very interesting course. So my advice to you is to ask questions. I know you're not going to do that in class. And talk to your professor, because believe it or not, they really want to help you, and what they want is your success. Like me, I want you to be successful too. Alright, another animal cell. I don't know why I included it there, but there it is. Oh, here's why. So if you look at this cell wall, the plasma membrane, you should know from Bio 1 and Bio 2 that it's made out of a bunch of phospholipids, and phospholipids, as you well know, contain a lot of carbon, a lot of hydrogen, oxygen, and phosphate, or phosphorus. And there you go. These are the types of carbon chains that we have: cyclic, branched, linear, planar. This is just to show you pretty much the elements that make up your cell. So what you should be taking away from this is that you've got a lot of carbon and a lot of hydrogen. What is not being shown here, though, is all the water that's in your body. So you know that you have a lot of carbon, a lot of hydrogen, a lot of oxygen from your water and the oxygen that you breathe. And you also have a lot of nitrogen. So that segues into the chemical elements of life, and these are the majority chemical elements of life. You've got hydrogen, oxygen, carbon, and nitrogen. You've got the most hydrogen. This is what you need to pay attention to. The amount of hydrogen that you have, oxygen, carbon, and nitrogen. So I guess just know that you've got a lot of hydrogen, a lot of oxygen, and the amount of oxygen that you have is greater than the amount of carbon. And naturally, you have the least amount of nitrogen. And these all amount to 99.4%. On your exam, I've seen a question like this before. So this is a slide from your PowerPoint slides that I would definitely want to remember. Just because this is like a gimme question, so it'll be helpful for you to know. And that goes to our first question without looking at the answer or the chart. So list the most abundant elements in the human body from high to low. So like we said, you have the most amount of hydrogen, so that should be your first pick, which means that B and C are both wrong automatically. So then it's between A and D. And what do we have more of, carbon or oxygen? And the way that I like to remember it is we have a lot of water in our body, and water is made up of hydrogen and oxygen. So naturally, we should have more oxygen than carbon. Also, there's like a statistic where it's like our body is made up of like 75% water. I don't know the actual number, but long story short, you got a lot of oxygen. So for that reason, the answer is D. Let's see. Let's see if I can use this thingy. Sorry, I'm learning how to use this little pen. I'll get there one day. Yeah, so the answer is D. All right. Okay, so this is another really important slide, and that's this one right here, the one that I'm talking about. Both of your lectures included it in their PowerPoints for a good reason. You really need to pay attention to this slide. So it's titled, What are the major ions of life? And don't freak out if you don't understand it. I remember when I took Biochem 1, I saw this slide and I was just extremely confused. I didn't even know how to read it. I think that just showed how dumb I was. But we'll go through it together. Alright, so on the y-axis, you have the milliequivalents per liter. You can literally just think about this as concentration. So you can replace milliequivalents with moles per liter, and then boom, that becomes molarity. Okay, so on the y-axis we have concentration, and on the x-axis we have blood plasma, interstitial fluid, and cell fluid. And the cell fluid is represented here on this cell, which is also labeled intracellular fluid. It's the same thing. And then interstitial fluid, which is the fluid between the cells, and then you have blood plasma, which is the fluid that's inside of your blood vessels. And so what we're going to be doing is we're going to be looking at each individual one of these, and we're going to see which is the most abundant ion in each one of these. So if we start with blood plasma, we can see, this is really important, so pay attention. We can see that our magnesium levels range from 0 molar to about 4 molar. Molar sounds like a lot. We'll stick with it. You'll get the idea. So if you see, we have from 0 to about 4 moles of magnesium 2+, which is kind of low. And then if we move up to calcium, which is this one over here, it ranges from 4 to about 9. It's becoming a little more concentrated, right? And then you have potassium, which ranges from 9 to about 15 milliequivalents per liter. So those ions are very low in concentration inside of your blood plasma, which is over here. And if you look, the amount of sodium that you have in your blood plasma ranges from about 15 milliequivalents per liter all the way up till 165 milliequivalents per liter. So someone in the review session that I hosted last week very astutely pointed out that the amount of sodium that is in your blood plasma has a lower limit of about 15 milliequivalents per liter and an upper limit of 165 milliequivalents per liter. So that is something that's very important for you to remember. It can be as low as 15 milliequivalents per liter or as high as 165 milliequivalents per liter. And then if you look, you also have bicarbonate, but that's not an ion, or carbonic acid, that's H2CO3. That is not an ion, but it's still found in a high quantity inside of your blood plasma. And so we'll go through those concentrations. It ranges from 165 all the way up till about 168, let's just say. So the amount of H2CO3 that you have in your blood plasma is as low as 165 and as high as 168. That's a pretty high concentration. I don't want you to think that that just because I'm going into specifics about this graph, that they're going to ask you on the exam which of these ions or which of these constituents is found in concentration ranges from 165 to 168. That's not what they're going to ask you. They're going to ask you simpler questions. You'll see what I mean. We're just going over how you should be reading this this graph. All right. So going back to blood plasma, if we'll look at the right column, the amount of protein that you have ranges from 0 to about 18 milliequivalents per liter. It's kind of low. And then you have the organic AC. I'm going to say that's acetate. Doesn't matter. Let's just go to chlorine or chloride. Chloride ranges from 26 till about 137 milliequivalents per liter. That's a pretty good amount of chloride, right? I mean, it ranges from as little as 26 till about 138. That's a pretty good amount. But bicarbonate, it ranges from about 138 all the way till about 168. So it has a much shorter band, and it has a much higher upper limit. I hope that I didn't confuse you by saying that. What I mean is chlorine or chloride can exist in a very small concentrations in the blood plasma or in very high concentrations, whereas bicarbonate, it exists in high concentrations to very high concentrations. So what should you be taking away from this? Your blood plasma has a lot of sodium and a lot of bicarbonate. That's it. And if you can now read the blood plasma one, then you can also read the interstitial fluid columns, and you can also read the cell fluid columns. And if you look at the cell fluid columns, your potassium ranges from, let's say, 55 milliequivalents per liter all the way up till 196. That's a lot of potassium, and this makes sense. For all those of you who took neuroscience and bio, you guys should know that the outside of your cell, the interstitial fluid, should contain a lot of sodium, and that the inner part of the cell should contain a lot of potassium. At least this is true for neurons, which they are cells. Okay, so number 2. Which of the following is the most abundant ion found in blood plasma? So let's look at the blood plasma columns again, and it's asking for the most abundant ion that's found in blood plasma. So straight away, H2CO3 That's not an ion, so we're going to immediately discount it. Also, it's not one of the answer choices, so there's that. But it's asking for an ion, so it could either be positive or negative. And so sodium, again, it's found as little as 15 milliequivalents per liter, all the way up to 165, whereas bicarbonate is found at concentrations of about 136 to about 168 or 165. I'm sorry if I'm butchering these numbers, but what you should be taking away from this is that bicarbonate is found in high concentrations to very high concentrations, whereas sodium is found from very low concentrations to high concentrations or very high concentrations. Alright, sodium's not one of the answer choices. So the answer choices are between chloride, sulfate, bicarbonate, magnesium, and phosphoric acid. So if we look at this, the one that is the most abundant, it's a toss-up between HCO3- and chloride. Yes. So the only possible answer choices are A and C. And which one do you think is the right answer? Yes, you're correct. The answer is C. And the reason for why it's C is because bicarbonate has a lower limit of 138 all the way up to 165 or 166, whereas chloride has a very lower limit. That just means that chloride is found in very low concentrations, that it can be found in very low concentrations, or it can be found at quite high concentrations. So, yeah. Alright, moving on. Number 3, the most abundant extracellular cation in the human body is zinc 2+, sodium+, calcium 2+, and potassium. So we're looking for the most abundant extracellular cation. So extracellular cation, that's going to be your interstitial fluid. So we want to look at this chart right here. And what is the most abundant cation? That would have to be sodium. Yes. So let's see where's calcium. That's low right there. And then there's also potassium, and that's also low, and so is magnesium. So the answer for number 3 is B. I guess I should mark all the right answers, not just the ones that I conveniently remember. I'll get better. Okay, so yeah. Also, I know that I'm not the best at explaining things, so on the comment section, please write if there is any particular part of this that I didn't explain correctly or that I didn't explain to your satisfaction. The whole point of this is to benefit you. So if I'm not doing my job and explaining things correctly or in a more efficient manner, then I should be fired. Please don't fire me. I'm talking to my bosses because they're watching this. But yeah, if you got any criticism, please put down in the comments. I want to become better. I know that I'm not the best, but one day I will be. Alright, so I got this from your slides. So heads up, you will need to know the properties and structures of the 20 common amino acids, and you will need to be able to draw a polypeptide chain. This is extremely important. A lot of you look at these amino acids and you think, I'll remember it, or I'll learn them next week, or I'll learn them this weekend. But it's not that simple. Not only do you have to know these amino acids, you must also have a relative idea of their pKa's, the pKa's of their side groups. Not all of them, there's some that you should have a general idea of, and we'll go through that, don't worry. I'm probably making it sound more convoluted than it actually is. It'll be easy. You just have to remember how to draw them, their pKa's, and their life story, basically, and you'll be fine. Okay, so for those of you who attended my review workshop, you'll see that at the very top left of the review packet that I gave you, I wrote something to the effect of Saint Rocky Ched. Okay, let's see. Okay. So I wrote something to the effect of Saint Rocky Ched. I'm so sorry. My handwriting's going to get better, I promise. Alright, so Saint Rocky Ched, it's a mnemonic, alright? And so when I was in Biochem 1, my classmates, they ended up coming up with this mnemonic, and the reason for that was because we didn't know whether or not our professor would be giving us the pKa's of the side chains. And so what we came up with, or what they came up with, which is pretty smart, was this mnemonic, and each one of these letters right here, each one of these letters represents the side chain, or each one of these letters represents the one-letter abbreviation of the amino acids, which you should know. So S is for serine. Let's see, that's for serine. I'll get better at this. Please forgive me. Let's see. Yeah. So S is for serine. I'll probably just circle or annotate with the mouse for now. Okay. So S is for serine, and then T is for threonine. R is for arginine. K is for lysine, and Y is for tyrosine. Okay, so it's extremely important that you not only know how to draw all of these amino acids, but that you know all of their one-letter abbreviations. On the exam, they're going to try to trick you. Okay, when I say they're going to try to trick you, it probably sounds like they are like their enemies, but they're not. They're just trying to test you, and they're trying to see how well you know the content. So, for example, if I were to ask you, what is the one-letter abbreviation for glycine, what would you say? You'd probably say it was G. Okay. But if I were to ask you, what is the one-letter abbreviation of glutamate, what would you say? The correct answer is E. The one-letter abbreviation for glutamate is actually E. Now, I know that doesn't make sense, but they may ask you a question like, what is the one-letter abbreviation of tyrosine? And because tyrosine starts with a T, you might want to say it's T. But the correct answer would be Y, the letter Y. So yeah, you want to know the one-letter abbreviation for all of the amino acids. You want to know how to draw them, because they may ask you as a free response question to draw an amino acid or a peptide. And you're going to want to know some of their pKa's. And so Saint Rocky Ched, it's the one-letter abbreviation of the amino acids who have ionizable protons. And what that means is that they have a side chain that can give up a proton. So just as an example, we'll start with letters E and D. So letter E, this is the one-letter abbreviation for glutamate, like we had just discussed. And letter D is the one-letter abbreviation for the amino acid, known as aspartate. And so these both have pKa values of, they both have pKa values of 4. So what this means is that their side chain, this carboxyl group right here, and this carboxyl group right here, their pKa is 4. Alright, going with H. H is for histidine. And if you look at this side chain of histidine, this has a pKa of 6. Just the side chain. We're not even discussing this carboxyl group or this amine group. Alright, going to C. Letter C corresponds to cysteine, which is right here. And cysteine, this sulfide group right here, has a pKa of 8. Alright, so I'm pretty sure you get the idea now. These one-letter abbreviations correspond to the side chain of the amino acid. More specifically, it corresponds to the pKa of the side chain of that amino acid. So S is for serine, that has a pK of 13. T is for threonine, that has a pK of 13. Remember, we're just talking about the side chains. We're not talking about the carboxylic or the amine group that is found in every single amino acid. R has a pK of about 12. K, which is for lysine, has a pK of about 10. And tyrosine also has a pK of about 10. So 13, 13, 12, 10, 10, 8, 6, 4, 4. I think these are really important for you to know. You'll be doing yourself a massive favor. Just in case your professor doesn't give you these pKa's, you'll be doing yourself a massive favor by remembering their side chain pKa's. You know, it's better to be safe than sorry. Okay, and so this is just a guide to the 20 common amino acids. I think this is a really great picture. Okay, so before we move on, I want to draw an amino acid, and I want to explain why it is drawn a certain way. Alright, I had to take my watch off because it's about to get real. Alright, so I'm going to draw an amino acid, and I'm going to draw, let's say, I want to draw glutamate. Where do I find my pen? There we go. That's horrible. Alright, I'm going to redo that. That's not good. Alright. Okay. So this right here is the carboxylic group of glutamic acid. This right here is the amine group. And I put an extra proton on it. But it wasn't wrong. I want to draw the, excuse me. I want to draw the amino acid completely neutral. Alright, so this right here is glutamic acid. And what is the one-letter abbreviation for glutamic acid? That is correct. The answer is E. Alright, so here's glutamic acid, and look at the way that I drew it. I drew it completely neutral, but, and just so you know, this is the right way to draw glutamic acid. You can draw it like this, You can also draw it using the Lewis structure formula, which I really don't like. You know, how people do that, and then, what is it, another carbon. Yeah, you can draw it like this. I really don't like this, but some people, they need, this is the structure that they need to use. But we're not going to use that. Okay, so this is the correct way to draw glutamic acid when it's completely neutral, and more specifically, you need to pay attention to this. This is the right way to draw glutamic acid if you are not given a pH. If they give you a pH, this is the incorrect way to draw glutamic acid. And this is what I mean. This is my question to you, what is the physiological pH in your blood? So the physiological pH in your blood, so physiological pH is about 7.3. And so what this means is that at this pH of 7.3, what I'm telling you is that at that pH, your glutamic acid will not exist in this neutral state. That's the most important thing for you to remember. A lot of people, they look at these amino acids and they're like, man, the textbook shows it to me completely protonated, or why does this have a positive charge and why does this have a negative charge? It has everything to do with the pH. Whenever they show you an amino acid that has charges on it, that's them letting you know that it's not neutral. I mean, of course, I feel dumb for even saying that. That's their way of letting you know that you're at a certain pH. And so what we're going to do is we're going to modify this glutamic acid based on this pH right here. So the first thing we need to do is we need to understand that the pKa of the carboxylic acid group that is connected directly to the alpha carbon. So this is the alpha carbon. This carboxylic group that's directly connected to the alpha carbon, this has a pKa of about 2.9. And this amine group that's directly connected to this alpha carbon has a pKa of about 9. Alright, and this group right here, a carboxylic acid, this has a pKa of about 4. Alright, so now you're probably confused. You're probably asking, why does this carboxylic acid have a pKa of 2.9 and this one have a pKa of 4? The reason for that is because pKa's are dependent, this is really important, pKa's are dependent on the environment that amino acid is in. So let's just take a tiny little detour to OChem 1. Let's look at this acetic acid, and let's also look at this acetic acid, which has 3 fluorines directly attached to it. Between this acetic acid right here and this acetic acid right there, which one do you think is the most acidic? Or which one do you think is more acidic? The correct answer is this one right here. And the reason for that is because fluorine has the inductive effect, which pulls the electron density in this direction, and which allows this proton to become freed. You don't have to, this isn't something that your professor is going to ask you, for the most part. I don't think so. Don't quote me on that. It's just really important for you to know that pKa's, they're subject to change depending on the environment of that group. And if we look here, this carboxylic group is really close to this nitrogen group, to this amine group, which lowers its pKa to 2.9. But this one right here, this carboxylic group, is followed by a somewhat long carbon chain, which increases its pKa to about 4. So what does that mean? It means that this carboxylic group is more acidic, hence the lower pKa. This carboxylic group is more acidic than this carboxylic group. Hopefully I was able to sell you on that idea. If not, go ahead and put a comment in the comment section and I'll try to make another video about that. I think it's a really important concept for you to know. Actually, let me rephrase that. It's an extremely important concept for you to know. I guarantee you it's going to show up on the exam. Not as a straightforward question, just, you know, we'll do a practice problem and you'll see what I mean. Okay, so once again, drawing amino acids, it's okay to draw it in the completely neutral form, but if they give you a physiological pH or if they give you a pH, you're going to have to change it. And so let's modify this amino acid based off of the pH that we're given. So the pH is 7.3 and the pK of this carboxylic group is 2.9. When the pH is greater than the pKa, you must deprotonate. And so for that reason, this carboxylic group now looks like this. It's got a minus charge on it. Okay. Now, going to the amine group, when the pH is less than the pKa, so look at the pKa, it's 9, and the pH is 7. When the pH is less than the pKa, you must protonate. And for that reason, the nitrogen gets an extra proton and it gains a positive charge. All right. And going on with the next carboxylic group, look at the pKa, look at the pH. When the pH is greater than the pKa, you must deprotonate. All right. So again, the top glutamic acid is the correct way to draw it when they just ask you to draw glutamic acid. But if they give you a pH, depending on the pH, here it's 7.3, this is the correct way to draw it. There was a student in class who asked about putting the nitrogen on wedges. The only reason I do that is to show chirality. I don't think your professor will test you on that. I just do it because it's a formality. And plus, I like Chem. But Biochem's a lot better, even though it's a little harder. But you can do it. Okay, so before we continue, I guess, how did we know that the pK of this carboxylic group was about 4? St. Rocky Ched, the one-letter abbreviation for glutamic acid is E, which corresponds to a pK of 4 for this glutamic acid side chain. Okay, I'm going to say this again because it's really important. pKa's are subject to change depending on the environment. So don't get married to these values of 4, 9, and 2.9. Understand that pKa's can actually increase or decrease depending on the chemical environment that amino acid is in. This is really important, okay? They might test you on this. It was on my exam. I'm pretty sure that's not academic dishonesty. I mean, I didn't give you the actual question, so Come on, give me a break. All right. Okay, so this is my note to you. It is not enough for you to know how to draw the amino acids. You're going to want to know their 3-letter abbreviation and their single letter abbreviation. Okay, let me take it one step further. You're not only going to want to know that, you're also going to want to know the pKa's of the side chains which have ionizable protons. So let's go back to St. Rocky Ched. These are the single letter abbreviations of the amino acids which have ionizable protons. And what an ionizable proton is, it's simply a proton that can leave. So if we look at glutamic acid right here, the proton can leave, right? That's how we drew it. We drew it with it left when it already left because of the pH. So the pH was 7.3, which was greater than the pKa of 4, so we had to deprotonate it. Thus, it's an ionizable proton. It's a proton that can easily leave. But notice how G, so glycine, isn't here. So there is no G in St. Rocky Ched. And why is that? The reason for that is because the R group, which is, it's this right here, this R group does not have an ionizable proton. It's just 2 hydrogens connected to carbon. And the pK of that is really high. It's like 20 or 30. So the pK is too high for us to consider it in St. Rocky Ched. Also, phenylalanine. Notice how the letter F for phenylalanine isn't here in St. Rocky Ched. And the reason for that is because the side chain doesn't have an ionizable proton. Yeah, so if you look at the side chain, there are no ionizable protons. The pKa of that benzene group is about 40 something, which is extremely high. If your physiological pH ever reached 40 something, chances are you're probably dead and you didn't even know it. So yeah. So St. Rocky Ched only has the 1-letter abbreviation of the amino acids whose side chains have an ionizable proton. Notice how I keep saying side chain, and the reason for that is because I'm not talking about the carboxylic group or the amine group. I'm only talking about this side chain. So I think St. Rocky Ched's a good thing for you to know, especially if you're studying for the MCAT or if you're taking Biochem 1 very seriously. Alright, moving on. Number 4. So draw the following amino acids, blank and blank, using line angle formula. Line angle formula has been what I've been using to draw the amino acids. So in class we used glutamate and phenylalanine. What is the 1-letter abbreviation for phenylalanine? Good job. It's F. Let's see. Okay, there we go. So yeah, it is F. Alright, so drawing amino acids. It's fun, it's simple. We both know those 2 things aren't true. Okay, so here's how you should start drawing every single amino acid, and I think this is the best way to do it. So the first thing you got to do is draw the carboxylic group, and then draw the amine group. And I'm going to draw the amino acids completely neutral until I'm given a pH. So again, whenever you're drawing an amino acid, draw the carboxylic group, then draw the amine group, and then draw the R group. So the R group for glutamic acid is 2 carbons and boom, another carboxylic acid. Alright, so the the main thing that you got to remember here is that if you can draw the carboxylic group here and the amine group, you've already won half the battle. The other part is actually drawing the side chain, the R group. Okay. So then we're going to move on to phenylalanine. So again, every single amino acid has a carboxylic group. They have an amine group. Excuse me. And this one is a benzene. Has a side chain. Alright. So then it's also saying to label each functional group and list the pK of each respective group. So the pK of this is 4, that's 9, and then that is 2.9. Okay, going on to phenylalanine, the carboxylic acid group has a pK of about 2.9. Here, I should have written that. About. This amine group has a pK, there you go, of about 9. And what did we say about the phenylalanine group? If it's not in St. Rocky Ched, which is F, right? Phenylalanine is F. If the side chain, if the amino acid one-letter abbreviation is not in St. Rocky Ched, we don't worry about it. pK is way too high, so we move on. Okay, and it's also saying to label each functional group. I'm going to leave that up to you. Alright, so building blocks and macromolecules. So if we look over here, we've got 2 amino acids, so amino acid 1 and amino acid 2, and they can actually come together to form a polypeptide. So if you see here, this amino acid and this amino acid came together, so they lost water, and really what they lost was two of these hydrogens, and they lost 1 oxygen, which became that water. So these 2 amino acids come together in a dehydration reaction. That's good to know. It's a dehydration reaction. And they form a polypeptide. Okay, now we've been going for quite a while, so you may be a little tired, but this is extremely important and I need you to pay attention. Whenever you put 2 amino acids together, you form a polypeptide, and what you should be paying attention to here is that you don't have to draw the chemical reaction of how they come together, like what nucleophilically attacks what, in order to get the structure right. All you have to do is understand that 2 amino acids come together, they lose water, and their peptide backbone has a N for nitrogen, has a C alpha or Ca for the alpha carbon, and a CO for the carbonyl. So for every single one of these amino acids, you're going to have one N, Ca, CO. So N, Ca, CO, and then because we have another amino acid attached, we have another N, Ca, CO. So NCACO is something that you need to remember in order to be able to draw polypeptides. So question number 4 was child's play. It was too simple. Now we will combine these 2 amino acids to form a peptide. Draw the peptide at physiological pH, which physiological pH is about 7.3, and label the functional groups and list the pK of each respective group. So the amino acids that we had were glutamic acid and phenylalanine. And so what we're going to do is we're actually going to, whoa, messed that up. We're going to put, sorry about that. That's enough, all right? We're going to put these 2 together, and they're going to form the peptide EF, okay? So this is the peptide that we're going to draw. So draw the peptide at physiological pH, and so the way that we're going to do that is we're going to take this and we're going to use the NCACO method. So for every amino acid, and we have 2, for every amino acid, you're going to draw one N, Ca, which is that, and then CO, which is this carbon, CO. And then N, Ca, CO. Okay, so all we've drawn so far is the backbone. For every amino acid, it's NCACO, NCACO. And then from this alpha carbon and this alpha carbon, you can actually draw the side chain. This is the side chain for glutamic acid. It's a carboxylic acid. And then for phenylalanine, it is a benzene group. Okay, so this is the peptide. And here we've introduced a new term. This right here, this is called the N-terminus. And now this right here, this is called the C-terminus. This is terminology that you should be aware of. This is really important. So this amine group is called the N-terminus, and this this carboxylic group is called the C-terminus. And if you see here, they labeled it as well. So this comes together to form the N-terminus, and that's the C-terminus. When they come together, you now have the N-terminus and the C-terminus. I'm repeating it because it's important. And I don't know if you guys remember, but the pKa of a free carboxylic group amino acid, so that pKa is about 2.9, but whenever you put 2 amino acids together, it is no longer considered a free amino acid, and that pKa jumps up to about 4. And that's really important for you to know. So please make sure that you know that the pKa of the carboxylic group of a free amino acid is about 2.9, but the pKa for the carboxylic group of a polypeptide is about 4. So there you go. So the pK of the N-terminus, it stays at about 9, and the pK for the C-terminus, it is now 4. Alright, and the pK for this glutamic acid is still 4. And the pK for this benzene group, it's too high. We don't have to worry about it. So let's draw this peptide at physiological pH. And so what this means is that since the pKa is greater than the pH for the N-terminus, that means that we are going to protonate. So that's NH3+. And notice how the pH is greater than this pKa, so that means we're going to deprotonate. And it becomes an O-. And similarly, over here, the pKa is 4, and the pH is 7.3. Since the pH is higher, we must deprotonate it. And that's that right there. So, let's see. So yeah, so we have a +1 charge on the N-terminus, and then plus a -1 charge from the C-terminus, plus a 0 charge from the phenylalanine, plus a -1 charge from the C-terminus. And so what this means is that the total charge on this peptide is -1. This is really important. So if you have any questions about this, go ahead and put them in the comment section down below. I feel like a YouTuber. Okay, So remember, when the pH is greater than the pKa, deprotonate. And when the pH is less than the pKa, you protonate. Alright. I have a wall which says all the stuff that I should harp on, so that's what I'm looking at. Okay, we're doing good. Alright, so what will be the net charge on the peptide stair when it is in a solution of pH 12? Okay, so S is for serine. Well, we're going to use the NCaCO method for every single one of these. So that's NCaCO, 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 and NCaCO. Remember, you're going to have one NCaCO, NCaCO for every single one of these letters. Alright, so S is for serine, which is this group right there. T is for threonine, which is this group right here. Oh, and I forgot these H's right there. Alright, A is for alanine, which is just a CH3 group. R is for arginine, 1, 2, 3. And E is for glutamic acid. Alright, so I drew everything neutral, and we're going to draw everything at a pH of 12. So the pK of this amine group is about 9. And so because the pH is greater than the pKa, this is going to be deprotonated. The pKa's of serine and threonine are 13. So if you remember St. Rocky Ched, 13, 13, 12, 10, 10, 8, 6, 4, 4. pKa's of serine and threonine are 13, and the pH is 12. When the pH is less than the pKa, you protonate, but with alcohols, you do not protonate them any further. I know that in OChem, you learned that you can still protonate alcohols, turn them into good leaving groups. That doesn't apply here, so we're not going to worry about that. So that contributes a 0 charge. That's a 0 charge. Alanine, it can't be protonated. That's a 0 charge. This right here is arginine, which has a pKa of about 12. So this means that the pH is equal to the pKa. So that means that some of this peptide will have an arginine that is protonated, in which case it'll be a plus charge, and some of the peptide will have an arginine that is not protonated. And so for that reason, instead of this having a +1 charge, because you'll have half arginine protonated, half that's not protonated, the overall charge is going to be +0.5. So again, the reason why we have that is because the pH is equal to the pKa. So this means that some of this peptide, which has arginine, will be protonated, and that's a +1 charge, and some other peptide will not be protonated, and in which case it'll have a neutral charge. So if you put 1 and 0, if you add them up and divide by 2, you get +0.5. So yes, the answer is yes, you can actually have half charges. Okay, and so this right here is glutamic acid, which has a pK of about 4, and for that reason we deprotonate this. And this is carboxylic acid, which has a pK, the C-Terminus, which has a pK of about 4. And so for that reason, we will deprotonate that one as well. All right. And so what are the charges? Let's see, the pH is 12, so this is deprotonated. So we have 0 plus 0, 0 from here, 0 from there, 0, 0, plus 0, plus 0, plus 0.5, plus -1 plus -1. Okay, and so what does that come up to? I'll let you do the math on that one. And that will be the charge on this peptide right there. Okay, so shown below is the structure of L-Lysine. The pKa values are also shown below. What is the pI of lysine? So pI stands for Isoelectric Point. And so the isoelectric point is the point at which is the P. Let me start over. The isoelectric point, which is pI, is the pH of the solution at which it will have a neutral charge. And I'll show you what I mean by that. So, shown below is the structure of L-lysine. The pKa values are shown below. What is the pI of lysine? So, in order for us to find the point or the pH at which a solution of lysine, so let's say this is our solution of lysine. So let's say this is our solution of lysine, and we want to find out at which pH it'll be completely neutral. All we got to do is use something I created called the box method. You may not like it, but it's the only way that I have to explain it. So if you know of a better way, please let me know. So what I do with the box method is I put 3 reversible arrows for every single pKa. This is I think the best way to find the pI. So you put 3 reversible arrows for each pKa, and you put them in increasing order. Okay, and so what we're going to do is we're going to find out what's the charge when the pH is less than 2.18. So let's say the pH is equal to 2. It's a number that's less than 2.18, so I can use it. So when the pH is 2, that means that the pH is less than every single one of these pKa's. And when the pH is less than the pKa, what do you do? What do you do? You protonate. And conversely, when the pH is greater than the pKa, you will deprotonate. Alright, so when the pH is 2, which is less than all these pKa's, what's the charge on the whole amino acid? It is 0, plus 1, plus 1, plus 2. That's the total charge. It's plus 2. But let's say the pH, we increase the pH and we increase it to about 4. So let's say the pH is now 4. Well, when the pH is 4, we are going to deprotonate this group right here because the pH is greater than the pKa, which is going to give this a minus charge. So now we have to add up all the charges. We have -1 plus 1, that's 0 plus 1. So we have a charge of plus 1. So now let's increase the pH again. Let's make it 9.5. When the pH is 9.5, what will you deprotonate? Will you deprotonate this or this? And the correct answer is this one right here. When the pH is 9.5, or any number between these two, you will deprotonate, which will make this neutral. And then your charge is -1 here, 0 here, and plus 1 there, which gives you a total charge of 0. And this is what we wanted. And we're going to take it one step further. Let's say we increase the pH again to 11. When the pH is greater than the pKa, you will deprotonate. And so for that reason, this becomes NH2. And the total charge is 0 plus 0 minus 1, which gives you a total charge of -1. Alright. And so now we can find our PI. We have to take the two pKa's, which are around the 0. So we take these two pKa's, and we're going to add them up and divide by 2. And this will be your isoelectric point, and I think the answer is B. All you have to do is add these up, divide by 2, and it should be B. Yeah. Okay. Moving on to number 8. All right. So we have a solution of 1 liter, and it's made by adding 0.5 moles of benzoic acid. So we have benzoic acid. Sorry for the bad benzene. And 0.5 moles of sodium benzoate. So I'm going to put my sodium benzoate over here, and I'm going to put my benzoic acid over here. All right. So we have a solution, and it's a buffer solution. And we know this because we have the conjugate base and the acid. And so it's made by adding this many moles of benzoic acid and this many moles of sodium benzoate and 100 milliliters of 0.3 molar hydrochloric acid. So what do you think that hydrochloric acid is going to react with? Is it going to react with the benzoic acid, or is it going to react with the benzoate? And it's actually going to react with the benzoate. That's why I put it on the left-hand side. I already knew what was going to happen. Yeah, so because this is a strong acid, it's going to fully protonate this benzoate. And so we have 0.5 moles of this. So that's the initial condition. Change equilibrium. And we're going to introduce 0.03 moles of this. And then we have 0.5 moles of that. So because we have 0.03 moles of strong acid, that means that all of this is going to deprotonate 0.03 moles of this, or it's going to protonate that many moles of it. So we're going to lose this much of it, and we're going to lose a quantity of this as well. And we're losing this because it's getting converted into this. So that means we're making 0.03 moles of this. So at equilibrium, we'll have 0.47 moles of that, 0 of that, and 0.53 moles of that. And from here, all we have to do is use the Henderson-Hasselbalch equations, which is pH is equal to pKa plus log of the conjugate base over the acid, which means pH is equal to 4.20, which is the pK that is given over here, plus log of 0.53 over 0.47. And so the correct answer should be 4.15. I know this because I just did the problem before I started recording this video, so I'm not a human calculator, okay? But yeah, you would naturally be able to get it if you punched it into your own calculator. Alright, number 9. What will be the pH of a buffer solution with a phosphoric acid ratio of 1 to 10? So what this means is that you have 1 of those and 10 of those. Alright, so how can we find the pH? Well, because we have the acid and the conjugate base, we can actually use the Henderson-Hasselbalch equation. And so that is pH is equal to pKa plus log of A minus over HA. So the main thing that you guys should know, or that you should focus on with this problem, is that you need to be able to use the correct pKa for the buffer solution that you're given. And notice that here you're given H2PO4 minus and you're given HPO4 2 minus. So now the question becomes, which of these pKa's must you use? Do you use this one, or that one? And the correct answer is pKa 2. And the reason for why you use pKa 2 is because you have H2PO4 minus as your acid and HPO4 2 minus as your conjugate base. If we would have been given H3PO4, which corresponds with this pKa, then the pKa one is the one that we would have used. So what will be the pH of this buffer solution? That's pH is equal to 7.21 plus log of the conjugate base to the acid. And how much conjugate base do we have? We have 10 parts of it, and we have 1 of the acid. So what this means is that pH will be equal to 8.21. And so the answer is D. Okay, number 10. We're almost there. Hang in there. Alright, what will be the pH of a buffer solution with a phosphoric acid ratio of 1 to 1? So anytime we have a buffer solution, just like how we did in problem number 9 and in problem number 8, whenever you have a buffer solution, you're most likely going to want to pull out the Henderson-Hasselbalch equation. That's pH is equal to pKa plus log of A minus over HA. Alright, so again, we need to look at our buffer and locate or identify which one of these is our acid and which one is our conjugate base. And so this right here, because it's got the 2 minus, that's our conjugate base, and the H2PO4 minus, that's our acid. The one that has the most protons, that's usually your acid. That's a good way to tell. Okay, so because this is our acid H2PO4 minus, we know that we should be using pKa 2. So pH, excuse me. pH is equal to 7.21 plus log of, we have 1 of H2PO4 minus, and we have 1 of HPO4 2 minus. So log of 1 over 1. And if you took college algebra, you'll know that log of 1 is equal to 0. And the reason for that is because when you raise 10 to the 0th power, you get 1. So there's an inverse relationship. Alright, so what this means is that your pH is equal to 7.21 plus log of 1, which is 0, so therefore your pH is 7.21. Good job if you got it. Alright, last one. This is a good one. So at what pH will the imidazole group of histidine be 20% charged? And so what you want to do with this one, or with this problem, is you want to imagine a solution that is full of histidine. So it's a solution full of histidine. And we draw the amino acid. I'm going to draw it completely neutral. Oops. Okay. Alright, so NH2, and then we have the imidazole group, which looks like this. Let's see. Yes, I drew it right. I still got it. Okay. So this right here is the imidazole group. And by the way, all the questions that I've made for this review, these are all questions that that are pretty exam-like. So it's not really about being able to answer the question, it's about understanding the concept. And so what we want to know is, at what pH will 20% of this solution, so let's say this is 20%, at what pH will 20% of this solution have a histidine, or the imidazole group, will have this charged? So we want 20% of it to be charged, and we want 80% of it to be uncharged. So essentially what we have is a buffer. If some of it is charged, which would be the acid, and the other isn't charged, which would be the conjugate base, you've got a buffer. And for that reason, we can use the Henderson-Hasselbalch equation again. And so we're going to say, so acid goes on the bottom, conjugate base goes on the top, and I'm going to modify this based on what we are given. So we know that the pK of the R group is 6 plus log of, I'm going to put imidazole plus, because that's the charge on this imidazole group when it's protonated with this nitrogen. And on the conjugate base, we'll have imidazole not, which represents a neutral state. So we want to know the pH at which 20% of it will be charged. So pH is equal to 6.0 plus log of 20% on the bottom. And so if 20% of it is charged, then therefore 80% of it is uncharged. Alright, and so going over here, this will represent a pH equal to 6.0 plus log of 4. Yeah, I did my math right, I hope. So that would be a pH of about 6.6. So at this pH, you'll have a solution of histidine, which has a imidazole group, and 20% of that solution will have the imidazole group charged, and the other 80% will have it uncharged. So that wraps up all the questions that I had. Once again, my name is Alfonso Flores.